pizza lunch. Today is my pleasure to introduce our speaker, Anna Barnacka, who's actually here as an Einstein Fellow, and she'll be talking about the high-energy universe and how we can constrain properties of high-energy universe using gravitational lensing. Thank you.
So today I will tell you how to take advantage in the signal processing to resolve high-energy universe and to improve angular resolution from 0.1 degree to 1 milliarc second. Extragalactic jets are the largest particle accelerators in the universe. They transport energy from regions close to massive black hole up to hundreds of kiloparsecs into intergalactic space. They produce radiation from radio up to very high energy gamma rays, and they are also known to exhibit very violent variability. And we assume that this variable emission is produced somewhere very close to supermassive black hole. This picture shows M87 jet pictured with a Chandra instrument. Thanks to improved angular resolution of Chandra instrument down to 0.5 arc second, we have been able to detect emission, increased emission by a factor of 50 in 2004. And thanks to improved angular resolution, we have learned that this huge X-ray flare was not originating from the region, from the core, from the region close to supermassive black hole, but was originating from the HST1 knot. The distance between the projected distance between the core and HST1 is about 60 parsecs. And at the same time, when the X-ray emission peaked, reached its maximum, we have also detected gamma ray flare. From some reason, there is a different order of my... So this shows the gamma ray excess map around the position of M87 during this huge flare. So the point sprint function at gamma rays correspond to about 0.1 degree, which in this case correspond to about 30 kiloparsecs, which means that in the resolution of a gamma ray instrument, we can fit entire M87 jet. So to resolve the emission for M87, which is the nearest extragalactic jet, we would have to improve angular resolution at gamma rays by a factor of 1,000. Future instruments will provide an improvement in angular resolution by a factor of few. An example of M87 makes us further wonder how frequently emission is not produced, this variable emission is not produced in the region close to supermassive black hole, but from distant nodes along the jet. And this is a very important question because we use those variable objects, which are gravitationally lensed, to measure time delays, which in turn are used to measure the Hubble constant. So if we have multiple variable emitting regions, this can be a source for systematics in the measurement of the Hubble constant. Then how does gamma ray jets look like? Because we cannot resolve them. And what is the origin of gamma ray flares? Gamma ray detectors cannot resolve the origin of the emission, and the answer to this question is crucial to our understanding of particle acceleration mechanism, because it's important whether the particle were accelerated close to supermassive black hole or further away. In all theoretical investigation, it is assumed that this emission is produced somewhere close to supermassive black hole. But M87 shows us that we have a reason to doubt this assumption. So what we will see if extragalactic jet would be gravitationally lensed. To us, we would see multiple images of the lensed extragalactic jet. And we would see those multiple images because between us and the distant BLAZAR with extragalactic jet, there is a lensing galaxy. And this lensing galaxy will split the light into multiple paths. And then when we have a flare from the jet, because the length of the path is different, and also we have a different gravitational potential, we would observe the same flare multiple times with the time delay. And this time delay depends on the position of the emitting region in the lens plane. And because it depends on the position of the emitting region in the lens plane, so if we can measure this time delay, then we can use it to find out from where the emission is coming from. So this is what we need to resolve high energy universe. So those are all elements of the method. So first, we can imagine that we have extragalactic jet like M87. So jets are huge. They are like hundreds of kiloparsecs. But the one which we are interested in are blazars. So their jet is pointed toward us under small angle of few degrees. So the projected size of the jet is about few kiloparsecs. Also, the Einstein radius of the lens, where the lens is the galaxy, is about few kiloparsecs, which means that we can fit the entire jet into the lens plane. Then, depending on from where the emission, this variable emission, originates, the emission will cross the lens plane at the different distance from the center of the lens. This will produce different gravitationally induced time delays between mirage images depending on where along the jet emission was produced. Then using the radio instruments and optical instruments like Hubble Space Telescope, we can resolve images of lensed blazars. So this is the example of one of the bright blazar B20218 and its observations with radio and Hubble Space Telescope. So these resolved observations, together with the measurement of a distance to the lens and the source, can be used to reconstruct the mass distribution of the lens. Then at gamma rays, we cannot resolve the source. But when we observe a flare, gamma ray flare, then the lens will curve the spacetime and produce multiple paths. And we will see the same flare multiple times with the time delay. And because the variability timescale of the flare is short, is of the order of hours to days, it's much shorter compared to the time delay. The typical time delays are of the order of weeks to months. So even the light curve is unresolved, we can resolve flares and we can measure the time delay. Then when we have a time delay and we have a mass distribution of the lens, so we know which time delay correspond to different position along the jet. So when we have a time delay at gamma rays, we can use it to find out the location of the emitting region. So this is more or less how it looks like, but what we really need to resolve the gamma ray sky is a lot of Monte Carlo simulations to be able to measure the time delay and find the right methods of the time delay measurement. And we also need a lot of signal processing. And we need even more Monte Carlo simulations to reconstruct the mass distribution of the lens. And this is what I will focus on during this talk. But first, before we put a lot of work into all the Monte Carlo simulations and signal processing, let's do some back-of-the-envelope calculations, and let's put M87 on redshift equals 1. Let's assume that there is a lens between us and M87, and let's calculate what would be the time delay differences depending if emission originates from the core or HST1. In this case, if M87 were at redshift equals 1, then the time delay difference between emission originating from the core or HST1 would correspond to about 2 days. This is a huge difference. So we can measure the time delays with much greater accuracy, which means that we can, using this method, we can distinguish from where the emission is coming from. That's not mine. And we have gravitationally lensed blazars, which are also gamma ray sources. One of them is B20218. So here you can see the radio contours of this source, where we can see well-resolved images, mirage images of the radio core, separated by the distance of about 330 milliarc seconds. And you can also see the Einstein radius, which is produced by the extended emission from the jet, which crosses the center of the lens. The information, because we see the Einstein radius, it means that jet goes through the center of the lens. So this gives us the projection of the jet. Also, we know that the source, this bright blazar, is located at redshift equals 1, and the lens is located at redshift 0.68. We have also measurement at radio, and the time delay at radio is about 10.5 days, and the magnification ratio between images, mirage images, is about 3.6. So we have a lot of information about the source. And also, at gamma rays, we have a beautiful light curves. So gamma ray detectors like Fermi have a horrible angular resolution, but they have an exquisite temporal resolution. Fermi survives the entire sky since 2008 and is able to produce the map of the entire sky within like 3 hours. So we have a perfect temporal resolution. And typically, Fermi detects about 1 photon from typical blazar. This blazar during the low state is pretty faint. We usually detect about 1 photon per 2 days. But from time to time, we have those huge flares. And in that kind of period, when those object flares, we can detect even 20 photons per day. So because we have such a uniform light, such a great and uniform light curve, they are perfect to measure those time delays. And this is what we are going to focus now. So we have this wonderful light curve, so let's try to measure the time delay. So method which I have developed to measure this time delay is called double power spectrum. So first, in the time domain, the observed signal is the sum at gamma rays is the sum of these mirage images, which we cannot resolve. So we see the superposition. So f over t from t is the intrinsic variability of the source. So we will see it represents the first light curve. Then the second component has the same temporal behavior, but is shifted in time and has a different magnification. So the sum of those two components represents well the lens, the light curve, gamma ray light curve of this lensed source. Then when we take the Fourier transform of the signal, we will get the Fourier transform of the intrinsic variability of the source, and also we will get the second component. So the Fourier transform of the second component gives us again the same Fourier transform of the intrinsic variability of the source, plus we have additional component due to the shift theorem. So the Fourier transform is composed of the intrinsic Fourier transform of the variability of the source plus additional component which arise from this delayed component. And you can see that this component has also part which includes the time delay. So when we take a power spectrum of the Fourier transform, we get the power spectrum of the intrinsic variability of the source plus additional component where the time delay arises as the periodic pattern with the period inversely proportional to the time delay, which means that when we take the Fourier power spectrum of the light curve, we will not see the time delay in the light curve as a peak. We will see it as the oscillation pattern. So to get the period, we have to take the second power spectrum. And this was the project I've been working on at the beginning of my PhD. So with my advisor, we get very excited that this method is so simple that why nobody thought about this? And we involve, and it was at Saclay, so there is a lot of engineers who work on building nuclear reactors and stuff like that, so they do a lot of signal processing. So we asked them about the opinion, and that was a mistake because they told us that actually this method is widely used in all kinds of areas and is known as a capture method and was published in '63. But we are still excited. So to investigate how to use this method, before we apply to the data, let's do some Monte Carlo simulations to see how well this method can perform. So we know that in the case of blazars, the variability is well defined by the red noise, or some people call it a random walk. So the red light curve is artificial. This is an artificial light curve represented by red noise. The green light curve is the same red noise, but with additional component, which also include the time delay of 20 days. And the green light curve is produced by taking this red light curve and the same light curve, but shifted in time and different magnification, and sum up to reproduce the time delay and the light curve that we observe at gamma rays. So in this way, we produce artificial light curve, which we can use to test the method. And here you can see, so the double power spectrum consists of two steps. First, we calculate the first power spectrum, where the time delay should appear as a periodic pattern. And then we calculate the second power spectrum from first power spectrum, where the time delay should appear as a peak. So it's difficult to see whether they are this periodic pattern or not. So the red point is the first power spectrum of a signal of the light curve, of the artificial light curve, without time delay. The green one is the same light curve, but with artificially induced time delay of 20 days. And then when we take the power spectrum, first for the green light curve, for the green power spectrum, we don't see even a hint of the time delay of 20 days. Red one was without time delay, and we don't see time delay, so this is what we expect. And then the blue one, the blue point, is the power spectrum, the second power spectrum calculated using the light curve of the red noise with artificially induced time delays, but we apply the signal processing. So if you don't use the signal processing, you may be completely overwhelmed by the noise and the intrinsic variability in the light curve. And after applying signal processing, we are able to see the signal very precisely. So because I got extra time, I can tell you more or less what we do, how the procedure of the signal processing look like here. So all steps I'm using are standard and well designed and well developed by other people. So this is nothing new. The signal processing field is very well established, so we cannot invent too much. I have learned that. And so the first step, you want to reduce this noise, the intrinsic noise from the light curve, and you want to be able to detect the time delay. So first, what we do in the first step, we remove the mean from the light curve. Then we also use the windowing. So the goal of the windowing is to balance between the sharpness of the peak when we have a periodicity in the light curve and the resolution of the spectra. So in this case, what we expect, we don't look for the peak. So if we apply the windowing, it would make the peak sharper, but it would also smooth the rest of the signal in the first power spectrum. In this case, because we are interested in this oscillatory pattern, we want to keep the maximum resolution of the spectrum, so that's why we use the rectangular window, which is basically, we don't use window at this step. Then we also we add zeros at the beginning and the end of the series to remove the spurious frequencies at the low frequencies, and also we double the points. So doubling the points is not adding any signal, but it allows us to remove the aliasing from the light curve by moving the Nyquist frequency into larger frequencies. So in this way, by doubling the points, we can remove the aliasing from the data. So after applying these few steps, you can see that now the red points is the second power spectrum. So this is in the second power spectrum, we should see the time delay. So the red spectrum corresponds to the light curve without time delay, and we don't see time delay. The green one was the artificial light curve with a time delay of 20 days. So after applying these few steps, we are starting to see the time delay at 20 days. But still the signal, the peak is very, very wide as compared to what we want to achieve. So in second step, we do further processing of the signals. So the intrinsic variability of the quasar is this red noise. So when we calculate the power spectrum, we have this trend. We have a lot of power at the high frequencies. So this introduces trend into the signal, and we want to remove this trend. So we flatten the light curve, but by taking the logarithm of the first power spectrum, and then we again extract the mean. So here you can see that after applying this step, red points we don't see. We basically remove everything from the light curve, from the signal without time delay. And now the when we calculate the time delay using the light curve with artificially induced time delay, we're starting to see the time delay. The peak is very sharp, but still we can improve it. So in the last step, we use windowing on the data, and again we add zeros to the beginning and the end of the light curve. And in this way, by adding these few steps, we have been able to extract the time delay very precisely. And all of those steps, and you can find well described in the appendix of one of those papers. So we have pretty well developed method which is tested with the Monte Carlo simulation. So we know that we can rely on it. So now we can look at the data. And this is the gamma ray light curve of our object B20218. So you can see that there was a huge gamma ray flare lasting for about 200 days. So there is a lot of variability. So by applying the double power spectrum, we've been able to measure the time delay in this light curve of about 11.4 days with an accuracy of about 3 hours. But again, question arises, whether it's a real time delay or maybe just a random fluctuation. To answer this question, we can again run Monte Carlo simulations and to find out how likely the signal arises from random variability in the light curve. So to investigate that, I ran Monte Carlo simulations and I produce about 1 million of artificial light curve which mimic the temporal behavior of a BLAZAR, of our source. And then based on this 1 million light curve, we can estimate the probability of getting a given signal. So the light curve which we produce here are without time delay, because we want to estimate how likely the time delay, the detection of the time delay can arise from the place where we don't expect it. And here, the points correspond to the gamma ray light curve. So you can see that in our case, the probability that this is just the random noise, that this such a signal would be produced by the random fluctuation is extremely low. And this corresponds to about 4 sigma. But you can see also that if you look into the light curve, there is a lot of structure in the data. So it's very easy to have some spurious detections because we have those flares. And of course, always we can measure the time delays between different flares. And this is what you can see here, that we have a lot of spurious peaks which correspond to these structures in the light curve. But then we can ask another question. So we have this light curve where we have a lot of flares, and between the flares there is always time delay. So we can ask whether when we have such a nice light curve of flares, whether the time delay is actually just the distance between those flares, or it's a real time delay, gravitationally induced one. So to answer this question, what we can do is that our light curve is about 200 days. So the real time delay will persist in the entire light curve. When the fluctuations, the time delays, when the fluctuations and the distances between the peaks would produce different time delays in different parts of the light curve. So we can cut the light curves into 3 pieces and then calculate the power spectrum on each of these light curves, on the slices, and then when we average it out, then only a true time delay will persist with the significant detection. So the other peaks, which are produced just by random distance between the flares, will appear only in the single segment. And when we average those segments, then the errors at those places will be big. And you can see again that only the time delay at about 11 days have a significant detection when we average it over large number of bins. So in this case, we have detected the time delay at gamma rays of about 11.3 days, and we are sure that this is significant detection and it's not produced just by random superposition of flares. And we know what we expect. So we have the lens, we have a lens there, so we can ask question, okay, but what we should see? We have because our light curve is limited, it's about 200 days. So, and also we know that we're looking for the time delay around 10 days. So the question is what we should see, what would be the expected significance of the detection for given light curve. And again, we can answer this question using Monte Carlo simulations. So in this step, we produce, again, about 1 million light curve, but this time with induced time delay. So we investigate different time delays from few days up to about 70 days. And we also investigated the magnification ratio between the images. So we can produce those artificial light curves with induced time delays. And then we can use the different method. We can investigate the double power spectrum method or autocorrelation method and see what we would see. What would be the expected probability of the detection at given significance level for a given time delay. And in this way also we can investigate which method is better. So here is the probability of detection of the time delay at given significance level using the double power spectrum. So we look for the time delay of about 10 days. And you can see that we expect that about the probability of detection of the time delay of 10 days at 4 sigma level is about 80%. And this is what we see. We detected the time delay at above 4 sigma level. So this is what we would expect for the double power spectrum. Then if we use autocorrelation function, then, and we would look for the time delay of 10 days, then we would have 80% chance that we would detect the signal at 1 sigma level. If we would like to use autocorrelation function and we would look for the time delay at 10 days, the chance that we would detect this time delay at 4 sigma level would be like 2%. So we can use Monte Carlo simulation to also to investigate how well different methods perform, and also what is the expected significance of the detection, because then if we detect the time delay at, let's say, 15 sigma, it tells us that this is not what we expect from the induced time delay, and we have to look for a different explanation for that signal. But in this case, for our source B20218, the time delay which we detect is consistent with what we would expect with given light curve and the given properties of the source. So we have well measured time delay. Now time to reconstruct the model of the lens. And in this case, again, we will use a lot of Monte Carlo simulations. So we look at this object B20218, and universe was very kind to us. So this is HST image around B20218. So you can see two images of the quasar, of the lens quasar and the small. There is also some contribution from the lens. And this HST image tells us that the lens is the single isolated galaxy, which makes the modeling very simple because we have to deal only with one tiny galaxy to reconstruct it. And we have a lot of information about the lens. So using the radio, we have the position of the radio core resolved with 0.5 milliarc-second resolution. Then we know that the source usually is located more or less between two mirage images. Of course, when there is some ellipticity in the lens, the position of the source can be slightly moved. So that's why we have to investigate the larger region of the source. Then we are also interested about what is the position of the lens. And in this case, we have some constraints from the Hubble images. So what we want to find out what is the model of the lens, and also what is the precise position of the lens, and what is the precise position of the source within 1 milliarc-second. So we have a lot of initial information which we can use for Monte Carlo simulations. We will start with the model which is called softened and parallel potential, because this model has a few parameters which we can investigate. So one of them is the core, the size of the core. We can also change the slope of the potential, and also we can add some ellipticity. So this movie, and what we want to look at is how well we are able to reconstruct position of the radio images and the time delay for a different position by looking into different position of the source and the lens and different mass distribution. So here are the radio contours of the radio image. So the blue points are our observation, and then the red points, which moves here, are the reconstructed position of the radio images when we change the index of when we change the slope of the gravitational potential of the lens. So we can see that even when we change slightly, by a tiny step, the slope, the differences that we get in the position of the reconstructed images are huge. So if we change the slope even by 0.05, then we get the position of the images moved by about 20 milliarc seconds, which means that which means that we can reconstruct the model of the lens and the position of the source and the lens very precisely, because the position of the images are very sensitive to the model of the lens and the position of the source and the lens. And as additional parameter, we use also the time delay. So we use the well-resolved position of the radio images. And to remove the degeneracies between different models, we also add the time delay. And even when we change slightly, even if we make a tiny change into any of those parameters, the change in the reconstructed position of the images is huge. So here you can see variation when the change of the reconstruct position of the images when we change position of the lens or position of the source only by 1 milliarc second. So this kind of calculations will be our input to Monte Carlo simulations. Because in case of Monte Carlo simulations, what we need are the set of observations, the model, and then we have to sample through parameter space. And we ran Monte Carlo simulations, and we got a lot of plots, a lot of numbers. But what is important here is that we investigated the range of parameters, which first three correspond to the model of the lens, then position of the source. We look for the position of the source and the position of the lens. And Monte Carlo simulations allow us to measure those parameters very precisely. But I think what is important in this slide is that we can run this kind of Monte Carlo, we can implement that kind of Monte Carlo simulation within a few hours by using available packages. So the only thing that we have to do is to write the function which can calculate the position of the images. Then we just need to specify the parameter space, and using those available packages, we can do those kind of simulations very quickly. So now we can look on how well our Monte Carlo simulations reconstruct the observations. So our observation was the position of the mirage images, image A and image B, the time delay and magnification ratio. So we have been able to reconstruct, using Monte Carlo simulations, we've been able to reconstruct the position of the image A up to 0.4 milliarc second. Also, our reconstruction of the position of image B is about 0.8 milliarc second. We are able also to reconstruct very well the time delay and magnification ratio. This tells us that the resolution of our lens now is about 1 milliarc second. So we have well-reconstructed position, we have well-reconstructed the model of the lens, and we have very well-measured time delay. So now finally we can take advantage of those measurements. So when we combine, so usually time delay and the position of the images and the lens were used to calculate the Hubble constant. But we know the Hubble constant from different probes. So we can use here Hubble parameter as a cosmic scale. And we can use the time delay combined with position of the images and the lens model to find the offset between the result emitting region of the radio core and the emitting region from where the variability, from where the flare was coming from, for which we measure the time delay. And this is what we find. So this is the Hubble space. So when we use the position of the radio core to calculate the Hubble constant, and the time delay reconstructed using the model of the lens, which is consistent with the observed time delay, we get the Hubble constant, the true value of Hubble constant. So the Hubble constant here is about 67. This is what we would expect. But now when we combine, when we use the resolved position of the radio core, the position of the mirage images of the radio core, and the time delay measured at gamma rays, and we combine it to calculate the Hubble constant, we get the Hubble constant of about 63. We know that this is a not true value of Hubble constant, which means that the emitting region from where this time delay originated, it's not at the radio core. And because we know the Hubble constant precisely, we can calculate that the distance between this radio core and the emitting region from where this gamma ray flare was coming from is about 51 parsecs. And these lines here correspond to about 1 sigma in the measurement of the Hubble constant from Planck. So the separation, the significance of the separation between the radio core and gamma ray flare is given by how well we can measure the Hubble constant. And in this case, the separation is about 3 sigma. And when we will have a more precise measurement of the Hubble constant from different probes, we will be able to separate the emitting region at even higher significance. And in this case, we know also that the jet is pointed toward the center of the lens. So jet, when we have a radio core here, then the jet is going in this direction, which means that the central engine must be in the opposite direction, which tells us that the radio core is far away from central engine. So to summarize, at radio we have an excellent angular resolution. At gamma rays we have excellent temporal resolution. The Hubble parameter gives us the cosmic scale. Gravitational lensing allows us to combine all of those above. But what is the most important, that Monte Carlo simulation and the signal processing make it possible to reconstruct the mass distribution of the lens with 1 milliarc-second resolution and allow us to measure the time delay very precisely. And what we have learned? We have learned that we have a multiple time delays, even from single source, because at radio we have a different time delay at gamma rays, which means that those multiple time delays can be a source of systematics for Hubble constant measurement. Then we've been able to obtain the special resolution at gamma rays of about 1 milliarc-second, which is which improves the angular resolution by 6 orders of magnitude as compared to current resolution of Fermi. And we have learned that this gamma ray flare was not originating from the radio core, as is commonly assumed, which means that the radio core is not at the central engine. And we have learned that the Monte Carlo simulation is the answer for all kinds of questions. Thank you.
So do you have any questions?
Monte Carlo is the answer.
Can you estimate the mass of the lens?
Yes, mass is a tiny spherical galaxy of the mass about 2 times 10 to 10 solar masses. So it's tiny. Because the Einstein radius gives us the estimation of the mass, and the Einstein radius is tiny. It's about 330 milliarc-second. So it's a tiny galaxy.
So I was surprised that the signal processing method or low power spectrum is so much more powerful than the autocorrelation method. It seems like autocorrelation should do comparably well. Do you have an explanation for why not? Why does it work?
Of course, because we apply the signal processing. And in the case of autocorrelation, it's a one-step procedure. Double power spectrum in the spirit is kind of similar to autocorrelation, except that we have those two steps. And in each of those steps, we apply signal processing. So this is what makes the difference, that we are able to add more processing. Take more advantage of the signal processing, yes.
And just to follow up on that question, wouldn't there be sort of analogous techniques you could do in autocorrelation, like some sort of filter to the time domain data that was, phase preserving before you took autocorrelation, and whether that could recover some sensitivity rather than
Yes. So of course, if you add them signal processing to the light curve, you gain a bit, but you don't have this additional step between the first and second power spectrum, where you can also add signal processing.
Do you conclude then from your studies so far that all of the knots observed in radio jets are due to the gravitational lensing effect?
For this
For this class of objects, because there are perhaps 25 blazars known with jets and multiple knots in the jets.
So for Fermi detects about more than 1,000 blazars, and 2 of them are gravitationally lensed so far. We know about 2 of them that are gravitationally lensed.
Are these selected then by seeing an intermediate galaxy image?
So yes, so we have radio observations, and based on those radio observations, we know that they are gravitationally lensed, because we see those multiple images. Those are very bright radio sources, so they were identified a long time ago as a gravitationally lensed systems.
Okay, thank you.
The delay is about 10 or 11 days. So you mentioned you are taking advantage of the excellent timing resolution of Fermi. But if delay is such large, then let's say Chandra or other X-ray telescopes should have a sufficient resolution to apply this technique, isn't it?
Yes, definitely.
Okay.
So the problem is to convince Chandra to spend a lot of time, like 20 days, looking for this object. So definitely, also, this method can increase angular resolution of new star by at least 2 orders of magnitude, and also Chandra. Also, you can improve angular resolution of Hubble Space Telescope.
Okay. I have one more question about the signal processing. It appears to be you may end up with a lot of parameters to apply those filtering, zero pitting, and all sorts of techniques. So how many parameters you have to sort of juggle to get the right output, or is it sort of more or less straightforward to apply?
So this is, I will say, of course, it's trivial and straightforward to apply. But in the end, actually, so my code in MATLAB is about like 60 lines to do the entire signal processing. Because again, MATLAB is designed to do the signal processing. So we can take advantage of method and tools which are already implemented.
So you're saying there's no fine knobs to need?
Not that many. It's I would say that it's only like 5, maybe less, maybe 4 places when you can play with parameters and to try to optimize them. Like for example, applying the windowing on the second power spectrum, on the first power spectrum, because we need to use some window, and there you have to play a bit. But again, this is very straightforward way. And when using Monte Carlo simulations, you have a handle on systematics and performance.
I have one more question. In the 11-day delay, you had another paper detecting similar delay. Is that
Yes,
same
from
method
Fermi.
or different method?
So they use autocorrelation.
Oh, okay.
And also by using autocorrelation, you can also see the same time delay. I also have used, in my paper, I also showed the result for autocorrelation, where they're without the correlation with all kind of methods, you can see the same time delay, but what is different is the significance. That the double power spectrum gives you a very high significance. When at the correlation you see the signal, but it's not. You cannot claim that it's significant.
Is there one more question?
I have a question. In your example, I saw your method produces two possibilities at around 20 days and around 10 days.
Mm-hmm.
So how do you exclude that possibility of time lag at 10 days? And the second question is, how do you measure the uncertainty of time lag at around 20 days? Do you run Monte Carlo simulation to calculate the uncertainty around the time lag?
And the error? So the error is from the fitting. I fit the position of the peak.
How do you compute the error on the position?
So because there are 2 points, but it's enough. So from the fitting of those points, it's the position of the peak. So I fit the Lorentzian profile, and this gives me the accuracy, the error of the on the peak, position of the peak of the Lorentzian profile. And the first question, so I selected it by purpose, the case where I see like a harmonic.
For example, in practice, if you don't know the true time lays at around 20 days, then how would you exclude those spurious signals?
So in this case, I run like 100 simulations to choose one where you can produce harmonic. So there is one reason behind it, which we can talk about it later, because I was wondering, okay, whether this method, how likely this method can produce harmonic. So when you have 2 time delays, you know that when you have one flare, you know that the only one time delay is real. And the time delay, which has a higher significance. And then if you see that this is just when you see that the second time delay is just a half of the first one, you can look whether it's a harmonic. And you can also run another Monte Carlo simulation to investigate the probability of having a 2 time delays just by chance.
Is it also possible that we see more than 2 spurious modes, like several spurious, not negligible signal?
So for that, we can run Monte Carlo simulations to see what's the chance of seeing in the one light curve like 2 significant spurious fluctuations. So you can construct Monte Carlo simulations and look for that. What would be the probability of seeing it? I guess that it will be very low, like 1 per million. But again, you can use Monte Carlo simulations to check the probability, how likely it is.
Okay, so I think we need to eat pizza now, but if you have any further questions, you can ask Anna over pizza. Thank you.
You should grab pizza now.
Very nice method and talk. I have one more question. How do you account for this is sort of weird, I guess, aliasing between the observing cadence of Fermi? Because you are not getting that many photons, right, per day. So Fermi is not looking at all the time, right? It's just
It's 3 hours. It takes 3 hours to take the entire
so there's
image.
some weird timing scale with the Fermi.
But they are short. They are very short as compared to the time delay we measure.
Okay. So, but in your simulation, you don't sort of try to simulate that has any effect on it?
So what I did, I was looking for a slightly different effect. That because sometimes you don't have a significant detection in your beam, but you have only upper limit.
Okay.
And upper limits are calculated based on the exposure. And exposure is like a huge sinusoid. It depends on the... And then you, when you correct for exposure, it introduces all kind of
weird peak, I guess.
satellite periodicities.
Yeah.
So what I did when I was measuring the time delay and when I was trying to estimate the significance of the peak, I was adding the same values of the. So I produced the light curve,
your
and
simulation,
then I added
include
the same,
those. Okay, all right.
the same values for for the places, for the beams where I had in the real light profound lateral limits, and I was looking how much the result would change. So there was not much variation. So the final conclusion was the same.
I guess that's fair
But
enough.
this is what I was doing as well. So I was studying, I was trying to find out how much effect from the satellite
Okay.
it can have. So
Yeah.
yes, I was investigating using Monte Carlo simulations.
Okay, that's great. Thanks. Yeah.
It's a great talk.
Thank you.
And I have one more question about micro lensing. Actually, your magnification ratio was constant. That doesn't depend on time.
Yes.
But if there is a micro lensing effect, that magnification ratio will change.
Yes. So
But in your case, are you only focusing on the case without some micro lensing effect?
So there are two things. So I didn't include microlensing here because I think I don't have to, because the variability timescale for microlensing is of your months to years. So the
So you mean
my
time
light
scale?
curve, but during the flare, if you have even microlensing, it would the magnification would be kind of constant in that time scale that we look for.
Okay.
And also microlensing doesn't change the time delay.
Sure,
even if you have a trend.
But your observation may be quite different. And your model assumption may be quite...
It wouldn't matter because actually I did kind of simulations by trying to introduce some additional pattern, and it doesn't change the time delay between the mirror images. So even
I'm not saying
Yes.
time delay changes, but... but
so
the way
actually,
to
the truth
estimate-
is. The truth is that it would help. The macrolensing would help to detect the time delay, because when you have this